So we're on chapter 15, section 6 in your chemistry book. And now we're going to be talking about acid-base titrations. So what is an acid-base titration? Well, when we look at that, it's what professional chemists do to find out exactly how much solution of base they need to neutralize an acid. In doing this, they use a system to add titration to add it to until the color turns. So, for professional chemists to find it necessary to determine the concentration, not just the pH of an acid or base in the solution, they use this method. For example, an industrial chemist might wish to test the concentration of hydrochloric acid in a solution used to manufacture plastics. To do this, he can withdraw a small amount of the solution and place it in a beaker. And he adds this standard solution, so they know, because they know the concentration of the solution, to the base into the beaker until the acid solution is totally neutralized, and that amount of base that's needed, he will know how much base is needed now to neutralize the acid that he's dealing with. And so this whole technique, of course, is called titration. And it's that basically the definition is the gradual addition of standard solution to a measured volume of solution until the unknown concentration of the reaction is complete. In an acid-base titration, equal numbers of equal acids and bases are needed. So titration is found out how you can neutralize, especially if you need to know, because pH may be an estimate, but you need to know, be more exact in your amount, especially when you're dealing with large amounts of acid that you need to neutralize. So here's a picture of one way to do it and how they're measuring it with the clamp and how the titration is set up. And on to what's in dealing with the equivalent point too. So the equivalent point is the point at which equal numbers of moles of base and acid have reacted, and it's called that equivalent point. When you get to that equilibrium point, that's called equivalent point, so you know. So if the addition of bases continued past this point, the pH will increase and it becomes less dramatic, but in that sense. So the plot of the how to plot this on a graph is here, and you can see these basically are basic the indicators here, and you can see how it gets to that point of equivalence and how it drastically then jumps up in the pH as the base comes. It jumps up. This is a process of doing the jumping, right? It jumps up to a higher base level. So it just doesn't go normally up. It goes up to this equivalent point. The equivalent point jumps up quite a few, and it drastically is increased in the pH of the base. This is working on the acid here, and then it will level out again. So that's the acid-base titration. As you can see, this is so important. You have this equivalent point so you know what's going on. And at this point, the changes are not known so radically. So you have as the changes get more radical, you see as the changes are changing, then right here's the radical change point, then it jumps clear up to the higher point. And you can use the indicators to figure this out too. So that's the plot of it, that equivalent point. Okay, let's see if I can, where's my, there we go, my little arrow. So as for the equivalent point, another thing that you need to know is what the end point is. So, and it's important to know, it says the choice of an indicator to signal the completion of titration when the equal numbers equal the acid depends on the pH region. And we kind of went over that there. And you can see how the colors in methyl red and phenolphthalein are also used in this situation as the titration. So they have these. The point at which an indicator's fully changed color is often called the end point, and it corresponds to the equivalent point as long as an indicator with suitable pH range is used. You have to use an indicator that has the suitable ranges. Remember we looked back there at the ranges of indicators? Let's go back and look at that so you can see what I'm talking about. Here's the indicators. So as the gradual jumps clear up past, 11, remember 14, it goes from 7 is going to be your mid point. Anything below 7 is going to be acid. Anything above 7 is going to be a base. And you can see how it drastically jumps up. So they use the right indicator. You have to write the indicator. The best indicator just for a regular would be litmus paper because it turns red with acid and blue with base, and it's right in that normal range. 7's right almost in the middle. So this is a good one to use for that. But when you're trying to figure out the higher base levels on what's going on, you might want to use one of these because they're only you can't detect anything below this range of 8, which is all base range. So it really matters what indicators you're using, and especially in titrations, to know where you're at in the midst. So it depends on the indicator used. So the purpose of a titration is to find the concentration of an unknown acid or base. The accurate measurement of the volumes of both reacting solutions along the accurate concentration for one of them allows us to find the concentration of the unknown. So basically, this is important. The equivalence of the reacted base have to equal the equivalence of the reacted acid. So that equation is up here. Volume of base times the normality base, and then the volume of acid times the normality of the acid. So this is the equation that you'd use in algebra. Volume times the normality being N. And that has to do with moles, remember? Except that we went over the moles in the last one. I'm not going to go over that whole situation, but moles and normality are almost the same except for those acids that are, or bases that are, are dihydrogen or diprotein or diprotonic, or triprotonic or plurals when we divided them out. So we did that in the last lesson, so I'm not going to go over that. So basically it's going to be volume times the normality, which has to do with the moles. So of the base and then the acid. Since normality is the number of equivalents, remember equivalents have to do with moles, per liter, the volume of the solution is in liters times the normality of the solution equals the number of equivalents. So basically you see, just knowing this, you can plug in your volumes and your normality numbers and you'll get the answer. So these can calculate. This is how they do the titration. It kind of seems complicated, but you can see how they're doing it to figure out how much concentration they're going to need in measuring it in liters now, because molarity is going to be the same as normality, which is going to be in moles. So here's an example so you kind of know. In a central or in a certain titration, you have this 32.15 milliliters, so not liters, but milliliters. And then you go on, and this was the normality. This is the measurement we got in that, and that's of a sodium hydroxide here. And onto it neutralizes. In neutralizing, here you have the sulfuric acid here. So neutralizing this 25 milliliters. So what are the normality and the molarity? So what we had to do is plug this in. We use this equation here to calculate, and we just plug these numbers in. Get your calculator out. So we plug in the volume. The volume is 32.15 milliliters. Remember, we're working in liters, but this is milliliters. And then we have, so we're probably at the end going to have to change it to liters. But here we have 25 milliliters, plug that in. And then you plug in these values here, this value here of the normality. So it's the V, N, you plug them in here. And then you're going to want to find this. This is the answer that we're going to find. So basically you can divide this by 25 milliliters here, cross out the milliliters. So we're not working with the milliliters anymore. We don't have to deal with that. And then you multiply this on your calculator, divide it by 25, and this is what you get. Since sulfuric acid is diprotic, remember, we're going to have to take this number and divide it. Again, the normality is twice the molarity, so N equals 2M. So this is because it has 2 hydrogen. Remember, we have to divide it out. And so we're going to have to divide this by 2. So we're going to take, we take this number and divide it by 2, and then we'll get it. Just because it's hydrogen is diprotic 2, so you're going to have to divide it by 2. This would be if it was equal, this number, but because we have that 2 hydrogen there, we're going to have to divide it. N equals 2 moles, and so that means we have to divide the normality by 2, and then you're going to get, basically it's plugging in your algebra problem, plugging in these here, and at the end you have to realize, okay, yeah, we have to divide it by 2 now because of this H2 in the acid. And that's the answer that we get. So it's really not that complicated. So this article is very good that everyone needs to read, especially those that grew up in the same era that I grew up, because I do remember the whole rigmarole about acid rain, in school and such, basically, giving us the terror that the end of the world will be coming because of acid rain, because we're going to have all of our water in our lakes polluted, and acidic. What are we going to do? We need to spend all this, similar to what we have with climate change now. But back then it just ran and rampant about acid rain. And it's kind of weird. It just kind of died out, and now we don't really talk about it anymore. Like, you guys really bumbled this, you environmentalists, that thought that you knew what was going on, and you really exaggerated things to that point, and then just think, okay, well, sorry, we spent billions of dollars on this, so that's what I think. So anyway, it goes on, it talks about, the reign of terror and the terror of acid rain. Everybody talked about acid rain, and acid rain doing because the air was so polluted that it was polluting our rain coming down. So, and this was the scourge of the skies. And in 1990s, anxiety ran high with people thinking we have to deal with this acid rain. So they developed what was called the Clean Air Act back then. And, it would have been fine, a Clean Air Act in helping pollution, but they went so all out in the area of acid rain. So what is acid rain? Well, all rain is naturally about, 5.6 pH, which is acidic. So rain has always been a little bit acidic. Why? Because there's dissolved carbon dioxide in the rain. So if you have carbon dioxide dissolving in the rain, and also due to coal mining and such, and the coal, burning of coal, especially in the industrial age of America, sulfur dioxide did also, go into the air. So we have carbon dioxide and sulfur dioxide, and nitrogen oxides too, and they all lower this, basically our air quality and the rain down a little bit to make it a little more acidic, where it's already acidic. So, but still, even if the rain was lowered all the way down to 5, which 5 is pretty acidic, 5 or less, this is only still just a very weak acid. So if you saw the table, it's not the acid that we think, oh, the rain is so acid. And usually the areas, yes, in certain areas, especially in the Ohio Valley, where there was a lot of coal put into the air by the industries, this did lower our the pH into an acid level there. So, but going on to that, also it wasn't just the measurement. When you measure the lakes and such, the measurement didn't really depend so much on the air. A lot of times, in the soil, it depended on what was in the soil and the drainage into the lakes. It's not just the air, right? So when you measure, it's not, if you have an acidic lake, is that because of the air pollution, or is that because of the surrounding land? It says in areas with mildly alcoholic basic soils, the acid rain is quickly neutralized. A lot of times the soils are alkaline, so they're basic. So when the rain comes down and hits the soil, it takes away the acid normally in many cases. But in certain areas, they were concerned, of course, and the presumed effect was that acid rain, is to fertilize the soil with this extra nitrogen and causing some trees and other plants to grow too quickly for healthy growth. What was that they said? Basically, they said, acid rain is going to make the alkaline come, and then all of a sudden, all of these trees are going to grow too quickly, and this is going to harm the lakes and rivers because of lowering their pH because of the acid rain, which we find out, where did they get that? So then they thought, well, then it's going to be possible for the fish and the fresh water and to live inside of them. So they exaggerated this into what was going to possibly happen, which did not happen. So the exaggerated warnings came in 1970s and 1980s. And people were saying, poison is falling out of the sky now. This is an environmental catastrophe. There's death traps. This is death traps. Our lakes are going to be death traps. And so the government agency basically then claimed at that time that the lakes were 10,000% more acidic than in 1940. Where did they get that? Government agency claimed in 1980 that the lakes had become 10,000% more acidic and predicted the number of dead lakes would double by 1990. They even put out photos of thousands of acres of dying forests to say this is what's going to happen with the dying forest due to acid rain and its toil. And they found out the pictures they took of dying forests were not due to pollution at all, but were due to bark beetles and stuff. So they took these pictures and they didn't even have anything to do with acid rain. So then legislators called for the reduction to slash the emissions of sulfuric acid and nitric acid to prevent, we got to prevent this national catastrophe. So they pulled back on industries. So, but was this really the case? In 1980, NAPAP, right here, National Acid Precipitation Assessment Program, and they spent a staggering $570 million in taxpayers' money, and hundreds of scientists and government agencies worked for 10 years. And they wanted to find out actually what is happening with this so-called acid rain. Well, when they did find out exactly the effects seemed very minimal compared to what they thought it would be. So it's less than 4%, which was out of 240 out of 7,000 lakes had a pH that was around 5, and the average pH was actually the same as the Industrial Revolution. So since, the early 1900s, our lakes have been the same. Despite all the rigmarole and all of the exaggeration, they were the same, and there was no current raise in average acidity of the lakes at all. And most had become acidic only because they're reverting back to the normal stage, because some of these lakes had been around areas that had been slashed and burned, in the logging industry in the 1930s, which was against the law now. So some of these lakes were just now reverting back, out of that state of alkaline to alcohol acid. So the alkaline runoff, because the ground and that was alkaline, like basic, and then so that the water actually was the acid and basic reacting there. The neutralization was causing the lakes to be more acid because they were coming back to normal. So, and actually to fix this was a very easy fix. All they had to do is add some lime to some of these lakes. and it would transform these lakes out of their acid type state that had nothing to do with, nothing at all to do with the air. They all had to do with what was going on the land. So the conclusions, basically saying that the soil chemistry was more important than the acid rain. In fact, it said here, as you read on here, it said the most acidified lakes were in Florida, where the rain was least acidic, while few of any acidified lakes were found in Ohio Valley. So now it's like, okay, Florida had most acidic, but the areas of Florida were not areas where there was a lot of air pollution. So what was causing this? It was not acid rain at all. It was actually what was going on in the land. And this was because most of the lakes in Florida were runoff in these areas, and not rainfall lakes filled with rain, but lakes that were running off from the land, which that brought in problems in certain where the land had been, infected in this way. So, so this whole acid rain, I always think when I think of acid rain, I think of the song Purple Rain, but, and that, not that it had to do with acid rain, but there was all of us, as going through this area of being a teenager and a young adult in this time, and, thinking, oh man, we're going to have to deal with this, the acid rain that's coming down. We're going to have to deal with our air pollution right away. Well, because the NPAP reported and contradicted the doom and gloom position on acid rain, the report was actually suppressed for a year and was not released after the vastly expanded Clean Air Act. So what happened here is a terrible, terrible thing. It's what government officials like to do. That is really not, basically so that they, it's really not being truthful to the public. Let's just say that. So what they did is they decided they already had this report that said that acid rain was not the problem. And so instead, they decided to put it aside, and they let the Clean Air Act of 1990 go through and didn't tell the public what the exact results were. And so, ironically, this law was spurred in large measure by the concern about acid rain, so now we had spent all this money for acid rain where we didn't need to spend it there. And so then they just kind of let it go and fade away. Let's not talk about acid rain anymore, and the public came and like, what about acid rain? Oh, we don't talk about that. Isn't that the way they do in politics? Yeah, we know. So, in summary here, the summary saying, it is unquestioned that air pollution can lower the pH of rainwater. We know that it can, and that we need to be careful, especially in our ecosystems. And also, air pollution can even erode stone monuments and statues. So we have to be careful. It's not saying that we have not to be careful, but we have to also know the magnitude of this effect appears to be much smaller than it once was thought. And so we need to look and, examine some questions remaining and go with the scientific evidence to suggest that acid rain is more of a nuisance than an environmental catastrophe. So they thought, oh, this is a catastrophe happening. Well, it's not. It's just more of a nuisance, and we need to watch it. So that's the deal on acid rain. So let's look here at some of the questions, kind of go over, see what we have there. What is the titration? We already discussed that there, how the chemist there would take small amounts. And here's a picture of the titration again. Where was that picture? So you can see. Right here, how they titrate out to find out the exact place where the base and the equivalent point where the base and the acid meet. That's why they do this titration, to find exactly what they need to cause to neutralize an acid, right? That titration point. So let's go back here, see if there's anything. Oops, getting ahead of myself there. The equivalent point, we already went over, that's the point where the acid and the balance become neutralized out together. And that point is sometimes takes a while, and we saw the picture of the graph, you know, where that equivalence point is. And of course we know acid rain, they thought was due to pollution of the carbon and sulfur in the air, and it became very exaggerated. So, and we already went over this. You can look back how we went with the moles and such. And this solution is calculate the normality and molarity. Remember that equation? Let's go back to that equation that we would use there. It's pretty easy because it's right here, this equation. You're just going to plug in the volume, which is in milliliters or liters, or how the volume is, and then put the numbers of normality that they gave you in these, and then you'll be able to find out what it is. But you always have to check and see, is this this here solution that we're changing to is from 1 mole of onto hydrogen. We have a diprotic right there. So in that diprotic here, we're going to have to divide at the end by 2. So let's look and see if that other one was a diprotic. If we have to divide by 2 or 3, or let's see. Okay, let's go back. I see where I'm supposed to be at. Nitric acid. So nitric acid is not, so we wouldn't have to change it. They gave you an easy problem there. You just have to plug it in to that equation that I gave you there, those numbers, and get the answer on your calculator. So that's it. So we're going to go on to the last section in just a bit.